Hello and welcome. When you look at a massive bridge or a giant crane lifting something heavy, have you ever wondered how engineers are so sure it's all going to hold together? Well, a lot of it boils down to one simple, really elegant rule for combining forces. Today, we're going to break down a true cornerstone of engineering mechanics, the parallelogram law. Let's dive right in.
So let's start with a really common problem. Picture this ring right here. It's being pulled by two different cables. One's pulling this way, the other is pulling that way. And they're probably pulling with different amounts of strength. The big question is, what's the combined effect? Where is the ring actually trying to go? And, maybe even more importantly, how much total force is that single point feeling? We need a way to find that one single force that does the job of both. And that's exactly the problem we're here to solve.
You see, in mechanics, we're always trying to simplify things. Instead of having to deal with 2, 3, or even more forces all pulling on one spot, we want to boil it all down. We need to find one single equivalent force that has the exact same effect. We call this the resultant force, and figuring it out is one of the most basic but powerful skills an engineer has.
And the main tool we use for this? It's the parallelogram law. Now take a look at this definition. It sounds a little formal, I know, but it's basically a step-by-step instruction manual. It tells us that the answer we're looking for, that resultant force, is literally the diagonal of a special parallelogram that we build using the forces themselves. So let's unpack what that actually looks like.
Okay, but before we start drawing anything, we have to get one really important idea straight. A force isn't just a number, like your weight on a scale. It's what we call a vector. And that just means it has two pieces of information. Magnitude, that's how strong it is, and direction, that's which way it's pointing. If you and a friend are pulling a heavy box, you can't just add your strengths together. It matters which way you're both pulling, right? The parallelogram law is the tool that beautifully handles both magnitude and direction at the same time.
So how do we actually put this law to work? Let's forget about equations for a second and just build the solution visually, step by step. It's actually pretty intuitive when you see it.
It really boils down to a simple three-step recipe. First, we join the tails of our force arrows. Second, we draw some parallel lines to make our shape. And third, we find the resultant. That's it. Let's see it in action.
All right, step 1. Here are our two forces. Let's call them P and Q. The most important thing here is that they're acting on the exact same point, which we're calling A. See how their tails are joined together? We draw them as arrows, where the length of the arrow tells us how strong the force is, and the arrowhead, well, that shows us the direction.
Okay, now for step 2, we're going to build the parallelogram. It's easy. From the tip of the arrow for force P, you just sketch a line that's perfectly parallel to force Q. Then you do the opposite. From the tip of Q, draw a line that's parallel to P. See where they cross? Boom! You've just made your parallelogram.
And here's the magic moment, step 3. You see that diagonal line that starts back at our original point A and cuts across to the opposite corner? That is it. That's our resultant force, R. This single arrow represents the total combined effect of P and Q working together.
Now let's be absolutely clear what this means. It means if you could somehow get rid of forces P and Q and instead just apply this one single force R, the object at point A would feel the exact same thing. It wouldn't know the difference. This is a perfect substitute. It's not just a cool geometry trick. This is how we figure out the real-world effect of multiple forces acting on something.
All right, seeing it drawn is one thing, but let's ground this with a quick example using some actual numbers. This is where you can really see how practical this is. So let's imagine we've got two forces. Force P is pulling with 100 newtons of force at an angle of 30 degrees up from the horizontal, and force Q is a little weaker, say 80 newtons, and it's pulling downwards at an angle of 20 degrees. Our mission is to find the single resultant force.
Now here's the really cool part. If you were to draw this out carefully on graph paper, using a ruler to make the 100 Newton line proportionally longer than the 80 Newton line, and a protractor to get the angles just right, you could build your parallelogram. And then you could literally just take your ruler, measure the length of that diagonal R, and use your protractor to find its angle. That gives you the answer. It's a graphical solution that works before you even touch a calculator. So you might be wondering, is this just a neat little exercise for a class? Not at all. This law is fundamental. It's at the core of how engineers design and analyze pretty much everything you see around you.
I mean, you see this principle everywhere once you start looking. Think about a crane hook with multiple cables pulling on it. Engineers use this to find the total load on that hook. Or imagine two tugboats pulling a massive ship into port. They have to calculate the resultant force to know which way the ship is actually going to go. Every single joint in a steel bridge is analyzed using this exact idea. It is absolutely everywhere.
Okay, so we've covered what the law is, how to use it, and where you'll find it in the real world. Let's finish up by making sure the big ideas have really sunk in with a few quick questions.
So first question for you. Can you take any two forces, no matter what they are, and always replace them with a single resultant force?
And the answer is yes, with one really important condition. They have to be acting on the same point. As long as the forces are concurrent, as we say, this law works every single time.
Okay, let's think about a special case. What if both of your forces are pulling in the exact same direction? What does our parallelogram look like then?
Well, it's a kind of funny thought experiment. The parallelogram basically gets squashed flat into just a single straight line. And in that case, the resultant is just the two forces added together. 10 newtons plus 5 newtons is 15 newtons in that same direction. The law still holds up, it just becomes simple addition.
All right, last question. Let's say you have two forces, and their strengths stay the same. What happens to the resultant force if you start changing the angle between them?
The resultant is definitely going to change, both its strength and its direction. And here's the key takeaway. The smaller the angle between the two forces, the bigger their resultant force is going to be. Just think about it. If you and your friend are pushing a car, you get the most bang for your buck when you're both pushing from behind in the same direction. As you start pushing from wider angles, your combined effort gets less and less effective. So, let's just wrap this all up. If you take anything away today, it's this. First, a force is a vector. It's got size, times, and direction. Second, the parallelogram law is our visual tool for combining any two forces at a point into one single equivalent resultant force. And third, this is one of the most fundamental tools we have for simplifying and solving problems in engineering.
So we've just spent all this time learning how to combine two forces into one. But what's really interesting is that in engineering, we often need to do the complete opposite. We need to take a single force and break it down into its parts, like its horizontal and vertical effects. That's called finding a force's components, and it's the next critical skill we're going to tackle. Thanks for joining me.